Our next unit is on polynomial functions. And boy, that polynomial function you see there looks crazy. Well, that's just like the generic term of it. I mean, if you think of a polynomial function, you might think of something like f of x equals 4x cubed minus 2x squared plus 3x minus 1. Or maybe like g of x equals 6x to the fourth minus 2x. Something like that. Those are all polynomial functions. Notice that the coefficients of x are all integers, and the exponents are all what we call the natural numbers. This big N stands for the natural numbers. The natural numbers are numbers like 1, 2, 3, they're your counting numbers. And the domain of a polynomial function is all real numbers. Sometimes it's written with a big old capital R. The domain goes from negative infinity all the way to positive infinity. So I want to ask you, of these 4 functions down below, which ones do you think are polynomial functions? Give it a shot. Alrighty, well, let's take a look at some of them. So first, we start with function A. We got a problem right off the bat because we know that we can't divide by 0. So for this one, the domain is that x can't be 0. And that violates our domain of all real numbers. So right away, this is not a function. And you might say the same thing with function b, because you got the x plus 4 on the bottom. But did you notice that x squared minus 16 can factor to x minus 4 times x plus 4? And that we can cancel the x plus 4s? So function b is really x minus 4? Yeah, all that's cool, but it doesn't matter. The domain takes precedent. So because the domain here is all x's but negative 4, function b is still a no. If you look at function c, I mean, there's nothing going on with function c, but it is a polynomial function. The exponent on x could be 0. This could be like term a0 up here. So that could be our function. And function d, if we were to write it with an exponent, it would be x to the 1/3 power. And there's a problem right away with our exponents, because our exponents have to be natural numbers, the counting numbers. We can't have a rational exponent. So that's no good there. There's a couple of characteristics of polynomial functions to be aware of. We call them the polynomial degree, the leading coefficient, constant term, and the number of zeros. So maybe you know some of these terms. Take a minute, see what you remember. All right, the degree of a polynomial is the largest power of the polynomial. So in this case, the largest power is this first term here. It doesn't have to be the first term, but in this case, the first term, because the exponent is 5. So in this case, it's a 5th degree polynomial. The leading coefficient is the coefficient of that power, of that largest power, we'll say. So in this case, our leading coefficient is 4. Again, it doesn't have to be first. It has to be the one with the largest power. The constant term in this case is the value that you have that does not have a variable on it. So in this case, it's that positive 1 at the end. It doesn't have to be at the end. So in this case, the constant term is 1. Because if we plug in an x value, the other 3 terms change, but 1 always stays the same. And lastly, the number of zeros is the degree of the polynomial. So this polynomial function has 5 different zeros. Wow. So there are 5 solutions for x that would make this equation true when we set x equal to 0, or when we set the function equal to 0. And that's what we're going to go into the next couple lessons. All right. So a couple things really quick here. Here's just what we call the parent functions. And remember, the parent functions, let's see if we can move some of these up a little bit. I don't want to erase. So the parent functions are those functions that we base everything else off of. And you've seen y equals x squared before. That's our parabola. But notice what happens to y equals x to the 4th and y equals x to the 6th. notice what happens when that power is an even power, when it's an even exponent. Yeah, it is kind of like parabola-ish, but notice that it starts to get a little flat here in the middle. Don't write with the pointer, write with the marker. Kind of gets a little bit flat there, and it gets more flat there. That's true about those functions with even exponents. And if you take a look at the ones with the odd exponents, do you notice that they can go from the negative all the way up to the positive? I mean, here's one that even goes before it. If we graphed y equals x to the first power, wouldn't that just be a line? So you can kind of see how our line gets a little curvy at x cubed, a little more curvy flattening out there, a little more curvy flattening out there. We're going to investigate why it gets flattened out in those values. So that's just some ideas about what those functions look like in general. One last thing about them is what's called their end behavior. And I'm going to go back for a second. The end behavior is what happens as the graph continues out to infinity. I mean, I was kind of highlighting the flattened out part, but look where this graph is going. It kind of goes up, or in the x to the 7th, it goes up and down. That's what our end behavior is. It's the behavior of the graph as x approaches negative or positive infinity. And what you notice that is if that exponent was even, if that largest power's exponent is even, the function is always remaining positive, and its behavior goes off to positive infinity. That was why when we had the graph of like y equals x to the 6th, as x gets really, really small, the y value goes off to infinity. Now, if you compare that with the graph of like y equals x cubed, an odd exponent, when that exponent is odd, negative x values make our y value negative. That's why it kind of goes something like that. But in a polynomial function, when x increases towards positive infinity, whether the exponent is even or odd, the y value goes off to infinity as well. We call that the end behavior of a graph. Let's talk about how we pull all these things together. So what I want to do is I want to take this function here, and I want to sketch its graph. So there's a couple things I'm going to do to help sketch the graph of it. First of all, I want to find the zeros of the function. So remember, the zeros are the values that make the function's output 0. It's like when we set it equal to 0. Well, that means I want to know what's the value of x that makes x plus 3 equals 0. So x would equal negative 3. Or when x minus 1 equals 0. So we'll say that for that 0, we get x equals 1. Or when we make the factor x minus 4 equals 0, we get x equals 4. A key thing here to notice is the relationship between the factors. Okay, these are the factors of it, and then the zeros or the roots of it. Notice that relationship between the factors and their zeros. Big thing to do. So this is where the graph is crossing the x-axis. So if I start building my graph over here, okay, I know it's going to cross at negative 3, it's going to cross at positive 1, and it's going to cross at positive 4. But I don't know much more that's going on with it. So I'm going to do what I call a sign chart. So I'm going to take some of my values like negative 3, 1, and 4. Now, I know the value of the function at negative 3. It's 0. But what happens if I go to the left of negative 3? Let's pick a number to the left of negative 3 on the x-axis, like negative 1 billion. Yeah, you can do like negative 4, negative 5. I like to do like really big numbers if I get a chance. So if I do negative 1 billion and plug it in for x, negative 1 billion plugged in here, negative 1 billion. If I plug in like 1 billion there, negative 1 billion plus 3 is a negative number. So I get like a negative. Now, negative 1 million minus 1, that's still a negative number. Negative 1 billion minus 4, that's still a negative number. So I get a negative times a negative times a negative, which is still negative. So what I know then is the graph is negative the y value is negative to the left of negative 3. Now, let's go between negative 3 and positive 1. If I go between negative 3 and positive 1, let me play with my signs again. A number like maybe 0 is a nice number between there. So if I plug in 0 for x each time, 0 plus 3, positive number. 0 minus 1, negative number. 0 minus 4, negative number. So positive times negative, that's a positive number. And that should make sense because negative 3 is a 0. If a graph is negative on one side of a value and positive on the other side, it has to be 0 at that value. Let's go between 1 and 4. Let's pick another number. Let's pick like a number like 2, for example. If I plug in x equals 2, I get a positive, and I get a negative. So that's going to be a negative value. All right, that's good. And if I plug in a number greater than 4, like a billion, I get a positive number. A billion minus 1 is still a billion. A billion minus 4 is still a billion. Think about it. If you're a billionaire and you give away $1, are you no longer a billionaire? So positive, that's all positive. Great. And finally, the end behavior. So I know that when I multiply my x's, it becomes some kind of an x cubed equation. So as x approaches infinity from the negative side, f of x approaches infinity. And as x approaches infinity from the positive side, f of x is approaching, we'll make an arrow there because it's approaching it, positive infinity. So there's my end behavior, there's my sign chart. Let's think about what this graph's going to do. And when I sketch it, I'm just sketching the x values. So I'm thinking, I know that to the left of negative 3 it's negative, so it's coming up like this. And then it has to go through there. But wait a minute, now it's positive. But when it goes to 1, it goes negative again, so it's got to go up, it's got to turn around, and it's got to go through 1. And then it keeps going down. But then wait a minute, the end behavior says it's got to go off to positive infinity. And I've got to cross over at 4 because 4 is a 0, so it's going to go something like that. So there's what my graph of f of x is going to look like. There's a sketch of that graph. Wasn't that fun? Oh, that's great. Let's keep rocking. So take a minute if you want, sketch this graph, find the zeros, make a sign chart, end behavior, do all that good stuff. I'll wait for you. Give it a shot. Try it. Accept the challenge. All right, let's talk about this. So for our zeros, did you notice that this is kind of like x plus 5 times x plus 5 times x minus 3? There's 2 factors of x plus 5. So what we then say is that the 0 is x equals negative 5 with a multiplicity of 2. Multiplicity of 2. That means that there's 2 solutions. There's 2 zeros that are the same. I wonder what that's going to do. There's also another 0 at x equals positive 3. So let's play the sign chart game. Here's negative 5. Here's positive 3. Let's pick some numbers and plug them in. Again, you know my first number I like to plug in like negative 1 billion. So if I plug in negative 1 billion for x, that's going to be a negative value. But then I have to square it so it becomes positive. And then I'm going to plug in negative 1 billion on the second set of parentheses. That's going to be another negative number. So let's think about what's going on. I got a negative squared, which is positive, times another negative, which is negative. But don't forget that negative on the outside there. That's going to be positive there. All right, let's keep on rocking. Let's check out some other things. Let's plug in a number between negative 5 and 3, like 0. That's going to give me 5, and I got to square it. If I plug in 0, I get negative 3. So I get a positive times a negative, which is a negative. But then another negative makes it positive. That negative changes to positive. Whoa! I got a 0 at negative 5, but the graph didn't cross it. What the heck's going on here? Boing. Let's keep going. Plug in a number bigger than 3, like a billion. If I plug in a billion, I get a positive number. Squaring it's positive. That's positive, but then I got to make it negative. All right. Now let's see what our end behavior is in this case. Notice this is an x cubed graph. This function is an x cubed graph, but it's really like a negative x cubed graph. So then our end behavior, let's think about it a little bit. As x approaches negative infinity, when those numbers get really, really, really small, okay, they're negative, but then I gotta change the sign again, so f of x is approaching positive infinity there. And as x approaches positive infinity, a big number cubed is a big number, but then we gotta make it negative. So that's gonna go to negative infinity. And that should make sense to you, because doesn't a negative in front of a function flip it over the x-axis? Oh, I get it. So I want to see what's going to happen here at negative 5. So my end behavior tells me that I'm coming down from the positive. I have a 0 at negative 5, so I got to touch the graph there. But it stays positive. Boing. So what I like to think about is if I get a multiplicity of 2, I call it a bounce on my graph. My graph hits the axis and bounces off. It's tangent to the x-axis. I should actually write that, right? Remember that term from your geometry? Tangent to, touching only once. And let's see, then it's going to cross over somewhere, and it's going to go through 3 and off to negative infinity. There's what our graph is going to look like as a rough sketch. Notice that bounce. Hey, let's try one last one. I'll pause it. Give it a shot. All right, let's go through our zeros. So because of this first root here, I know one of them is at x equals 0. And again, that's a multiplicity of 2 because it's an x squared. I also have 2 of them at x equals negative 4 with a multiplicity of 2. Ooh, this is interesting. X squared plus 4. If I want to set that equal to 0, let's see, I got to subtract 4, so I get x squared equals negative 4. I get x equals plus or minus 2i as the roots. Oh, mama. Eek. Plus or minus 2i, yikes. And then if I do x squared minus 4 equals 0, you can factor it, or you can add 4 to both sides, get x squared equals 4. So these solutions are plus or minus 2. Okay, this is going to be interesting. I have imaginary roots. What do? We get rid of some of this stuff now. Well, we proceed as we did before. But understand that the only ones that we can really identify on the x-axis are the real zeros. The other imaginary ones are off somewhere, and maybe that's going to be an exploration for another day. All right, let's do our sign chart. I got a value at negative 4. I got a negative 2. I got a 0. I got a 2. Remember, I can only do the real ones. I can't do the imaginaries. So it looks like if I multiply all these x's together, I get 8 x's and x to the 8th eventually if I multiply it all out. So that's going to be, if I plug in like a very, very, very negative number, I get a positive, I get a positive, positive. When it's less than negative 4, it's positive. Think about how when you plug in a number between negative 4 and negative 2, like a negative 3. If you do that, this is still going to be positive. That's going to be positive. This is still positive. That's positive. And that should make sense because of the double root, the multiplicity of 2. It's going to bounce there. But then at negative 2, or once it goes to 2, let's see, between negative 2 and 0, like negative 1. If I plug in a number like negative 1, let's see what happens. That's going to be positive. Negative 1 plus 4 is 3. That's positive. Negative 1 squared is 1 plus 4, that's positive. 1 minus 4, that's going to be negative. So, okay, there's only one root. My sign's going to be negative now because it has to go through the x-axis. If I go between 0 and positive 1, I'm going to get basically the same thing. So it's going to be negative again, which is good because I got two zeros at x equals 0. So it's going to bounce off the x-axis there. And then if I plug in a really, really, really large number, I get a bunch of positive values. So that's positive there as well. This graph we said works out to be like an x to the 8th. So as x approaches negative infinity, f of x approaches infinity. And actually if we do a plus or a minus, it's still true. Our sign chart kind of confirms that. Let's check out this graph. So it's going to be 1, 2, 3, 4, 1, 2. So we're going to come in from negative 4. We're going to bounce, boing. We're going to go through negative 2. We're going to bounce at 0, boing. And then we're going to go up through 2. Wow, that's a cool looking graph. Man, nice things there, friends. And those roots of plus or minus 2i, where are they? Oh, they're imaginary.